testing on YouTube, testing on YouTube. Test. Test, 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 test. Test, test, test. Test. Testing on YouTube. Testing on YouTube. Testing on YouTube. Come on. Why is this not streaming? All right, there we go. Audio's working too. Nice. All right, there we go. All right. Last one. Make sure this works on X. Testing on X. Testing on X. How's it going, Christopher? How's it going, Sarah? How's it going, Akram? How's it going, Exploring Lord Sheba? Dark Matter, Eunice. How's it going, everybody? Pursuit. Dan. Akram again. All right, should be live on X any second now. How's it going, Day? All right, let's confirm that the audio works on X, and then we'll get started. Broadcast is not available. Broadcast is not available. Get your servers figured out, X. Hire some Netflix people. All right, let's confirm that the audio works. Okay, perfect. It's working. Or YouTube people. I don't know what. I guess YouTube and Netflix are probably the best video streaming sites. All right, I'm gonna take a sip of water and then we'll start this. All right, welcome everybody to another Hoopos stream. We're going to be going into the world of multimodal models today. So building multimodal models. Multimodal models is a little bit of a tongue twister, but we're going to be centering on 3 different papers that came out. So these 3 different papers represent kind of different views of where we're at with multimodal models. And what we're really trying to do here is kind of guess where this is all going, right? So the first one that we're going to be looking at is called Chameleon, which is Mixed Modal Early Fusion Foundation Models. This is from Facebook AI Research, aka the Meta Team Zuck, if you want to think of it that way, 16th May 2024. The other paper we're going to be looking at is What Matters When Building Vision Language Models. This is from Hugging Face, so this is kind of like the open source multimodal model contingent. This is 3rd May 2024, just a little bit earlier than the Facebook paper. And then the last paper that we're going to be looking at is going to be Mirasol 3B, a multimodal autoregressive model for time-aligned and contextual modalities. This is Google, DeepMind, Google Research, same people, 3rd April 2024. So this paper has actually been published a couple times. It was first put on arXiv last year, and then they've been kind of publishing updates. But these are the 3 papers we're going to be looking at, kind of representing the 3 different, I would say, leaders in this space. You got Google, you got Facebook AI Research, and you got open source represented by Hugging Face. Of course, we're missing OpenAI and Microsoft, but you know they don't publish their research, so we have to guess at what they're doing. All right. Damn, you guys are already starting off with questions here. How's it going? Sunshine, Pursuit, Dark Matter, Tomcat. Question from Dark Matter. What is the difference between multimodal and multi-agent? Okay, so what is a modality? A modality is something like images or text or speech, right? So each one of those types of data is called a data modality. So a multimodal model, multimodal means that it's using multiple modalities, right? So in the case of these two papers here, that's going to be text and images. So it's doing text and images at the same time. Okay. Let's start with the abstract here. Chameleon is I'm going to actually skim through it a little bit too, because I realize that reading these abstracts entirely is a kind of a bit of a waste of time. So Chameleon is a family of early fusion, token-based, mixed modal models. So that's a lot of different adjectives, but we're going to learn what all of those mean in the paper below. It does a bunch of things, such as visual question answering, image captioning, text generation, image generation, and long-form mixed modal generation. Mixed modal generation is going to be the kind of cool new functionality that this has, right? Where in visual question answering, you get maybe a picture, a question, and then you answer with text. Image captioning, you're answering with text. Text generation, you're answering with text. Image generation, you're generating images. But this mixed modal generation, that's going to be the new capability, which is generating interleaved text and images, right? So that's pretty powerful and pretty new. And not only is this a VLM, right, within that VLM space, I guess we should almost call these multimodal models rather than VLMs, because VLMs almost feel like yesteryear technology. But this is going to outperform Llama 2 in text only, which is kind of crazy. And it's going to match or exceed the performance of much larger models, including Gemini Pro and GPT-4V. So that's pretty... Ooh, what just happened here? Google Chrome help. I don't want that. This is pretty important, because now what this means is that this is the new state-of-the-art vision language model, multimodal model, right? I guess GPT-4o is supposedly better than GPT-4, but is it better than GPT-4v? So if Chameleon is better than GPT-4v, it might even be better than GPT-4o, but we don't really know yet. So we're going to say potentially state-of-the-art multimodal model. Okay. The interesting thing about Chameleon is that it's going to be trained from scratch on an end-to-end fashion on an interleaved mixture of all modalities, right? And they need to train this from scratch because they're going to be using this early fusion approach where all modalities are projected into a shared representation space from the start, allowing for seamless reasoning and generation across modalities. Okay. So let's take a pause there to think about what does this actually mean. So what this means is that this model is taking these different modalities. Here you have the modality of text, here you have the modality of images, and it's almost immediately turning them into tokens. And these tokens are then being fed into this mixed modal autoregressive LLM, or language model, large language model. Now they're just calling it language model. But this is very different from what we've seen in the vision language model space up until now, right? And I think this Hugging Face paper kind of shows you, is a pretty good representation of what we've seen up until now. And in vision language models today, the way they usually work is that you have a vision encoder and then you have your language model, right? So the vision encoder is something that has been trained completely separately from the language model, right? The vision encoder might be something like Dino or Clip, right? Which is trained with some maybe masked reconstruction or contrastive language image pre-training, or like maybe it's just literally just a ConvNet that has been trained on ImageNet. And this vision encoder is separate from this language model. This language model might be something like Llama 1 7B or Mistral 7B. And what pretty much everybody has been doing up until now is kind of gluing these together. So you have a pre-trained vision encoder, you have a pre-trained language model, and you create an additional little bit of parameters here. So this little projection layer, sometimes called the projector, the adapter. There's been a couple different names for this particular layer here, but you're kind of performing this type of surgery where you have two pre-trained models, one for vision and one for language, and you're creating this projector that projects the vision representations into little tokens that match what the language model wants. And then you maybe mostly just tune this, or maybe you tune a little bit of this. You maybe push a little bit of gradients here, push a little bit of gradients here, but largely you're just gluing these two pieces together, which have been trained separately. Chameleon is different because it's trained from scratch in an end-to-end fashion. So no longer are we doing this kind of like gluing a vision encoder into a language model and then just fine-tuning a little bit. We're now training these things from scratch with mixed modal data, and the modalities are going into tokens almost immediately. So you see here how this image is not being fed into an image encoder. It's just going through a tokenizer, and then those tokens are just being fed straight into this language model. You can't do that if this language model was pre-trained. So you're going to have to train this from scratch. Okay. But obviously, if you're Meta, you have a huge amount of GPUs available, so you can do this, right? The reason that people weren't doing this before is because they don't have the amount of GPUs and the money required to train these things from scratch. So they're relying on this vision encoder, which was trained from scratch by Facebook if you're using Dino, or was trained from scratch by OpenAI if you're using Clip, and you're using this language model, such as Llama, which was trained from scratch if you're Facebook. So Hugging Face and pretty much the rest of the vision language model community has been relying on the fact that they're using these pre-trained models that are trained from scratch by someone else, and all they have to do is just train a little bit just to make sure that this projector is good, which is reasonable, right? You can do that with just a small little cluster, maybe if you have a cluster at home, I guess, but that's a completely different beast from what Facebook did here, which is train these things from scratch, and they train Chameleon 34B, so 34B is kind of like the middle size. They have a smaller one, Chameleon 7B, and then they have a Chameleon 34B, on 5 times the number of tokens as Llama 2, enabling a new mixed modal application while still matching or even outperforming existing LLMs on unimodal benchmarks. So that's pretty powerful, right? Because we always talk about this idea of transfer, right? Where, okay, if you train on one modality, you're going to generalize or be able to transfer into a new modality. But here we're finally starting to get some good data on this, right? What they're showing you here is that training on mixed modalities, interleaved mixtures of image and text and code, you're going to get better performance on unimodal benchmarks. So training a language model on purely text is going to be worse than training a multimodal model on text and images and whatever other modality, right? So interleaving these modalities increases the variance of your data set, and there's information in images that you can't get from text, and then there's information in text that you can't get from images, and really combining those together in this early fusion approach is going to lead to stronger models than just training them individually and gluing them together, which is kind of what we've been doing up until now. Okay. Chameleon 34B achieves state-of-the-art performance, outperforming Flamingo, Idifix, and Lava. Idifix is actually this one. So this is the paper for Idifix 2, but Idifix would be the original one. Competitive performance on text-only benchmarks, and Chameleon 34B substantially outperforms strong baselines like Gemini Pro and GPT-4V in pairwise comparisons, which are the gold standard, right? So sometimes in these benchmarks, right, especially the kind of more automatic benchmarks where it's just like some test that you're running, those can be gamed in a little bit of a way. You know, you can overfit to them, you can kind of cheat on those. But these type of benchmarks, which is you have a human evaluator, you pay some third-party service to have a bunch of people sit there and compare the outputs of one model to another. This is kind of the gold standard, right? Because it's like humans who have no idea which model is which, they're deciding which one they like more, and here you go. Here's the evidence. Chameleon 34B beats GPT-4V. 46% of the time, people prefer it. 30% of the time, they think it's about the same. And 22% of the time, they think GPT-4V is better. So you see here the fact that this green is very small means that it basically is the state of the art. Okay. Let's keep going. Let's see if there's any questions. Damn, you guys are already talking here. Is there a clear difference between early fusion and late fusion? Yeah, there is. That's kind of what I was describing, right? Is that late fusion, they don't call it late fusion, but that's basically what people do now, is where you're kind of relying on this vision encoder to turn this image into a set of representations, and then you're going to take those representations here, they're called hidden states, and turn them into little tokens to feed into an LLM, right? So you can kind of think of this like you're fusing it at the end right before you feed it into the LLM, versus here in Chameleon, you're fusing them almost immediately, right? You're basically turning the text into tokens, but now it means that you have to train this from scratch, because or else if you just had some language model here, it would have no idea what the fuck these image tokens were, right? Okay. So whenever they say interleaved, right? They say here interleaved mixed modal generation. What they're saying is that the images here, they're inside the text, right? So like you see here, it's a bunch of text tokens, text, and then suddenly it says image, and then it says text. So from the perspective of the model, it's receiving like a mix of these things, right? It's seeing text token, start image token, image token, image token, image token, image token, start text token, end image token, text token, text token, text token. So there's no specific order, right? It's not like it needs to have an image and then a piece of text. It's like you can interleave it. And it's not just the input, right? So it's not like the input is text and image, but the output is also interleaved. And that's the fucking crazy part, is that it's outputting interleaved text and images. So it's like text token, image token, image token, image token, image token, text token, image token. So we haven't really seen that, right? GPT-4v does not do that. GPT-4v can consume image tokens, but it outputs only text tokens. So this type of interleaved generation is new. Okay. How do you make a data set for this? This is a question from Dan Seath. We're going to look into it. So luckily for us, Meta is pretty open. They're very open about what they do. So this paper is really good. They basically tell you everything that they do, how they train it, what they train on, and so on. So we're going to really dive into that. So step one is going to be the tokenization, right? So the tokenization is how do you turn just a raw sentence of text into text tokens, and how do you turn this raw image into a bunch of image tokens, right? So how do you make that a sequence of tokens, which is what you can consume with a transformer, right? A transformer is a sequence-to-sequence model. It needs to consume a sequence and it needs to output a sequence. So you need to turn your text, your sentences, into a sequence of text tokens, and you need to turn your images into a sequence of image tokens. Okay, so they're going to train a new image tokenizer and a new text tokenizer. And, right, we've learned from Karpathy that tokenization is very important, and you shouldn't just gloss over it. If you're going to be putting in hundreds of thousands of dollars to train a new model from scratch, it's worth training a new tokenizer, and Facebook did that. Okay, so this new image tokenizer is going to encode or consume 512 by 512 images, which is pretty good, into 1024 discrete tokens, and the codebook size is going to be 8,192, right? So when your language model is consuming tokens and it's autoregressively outputting tokens, what it's really doing is it's deciding which token out of a set of possible tokens, right? So these tokens are not continuous. There's not an infinite amount of tokens. There's a specific codebook or vocabulary of tokens that are possible. So there's only 8,000 possible tokens that you can choose from to describe an image, right? So an image is going to be a sequence of these tokens, of which there's only 8,000 possible tokens, right? So you're limiting the number of tokens there. So in terms of the image tokenizer, your codebook size is 8,000. But for the text tokenizer, your vocabulary size is 65,000. So this lets me know that we're still in the early days here, right? Because to me, if you ask me where we're going, I think that the codebook size for visual tokens will eventually exceed the codebook size or vocabulary size for text tokens, right? The vocabulary size of text tokens at 65,000, that's the result of multiple years of iteration, right? We saw vocabulary sizes of 30,000, then we saw even some bigger vocabulary sizes like 100,000, but now it's kind of stabilized at around 60,000-ish, right? But vision tokens, we're still early days, right? It feels to me like 8,000 is not big enough. At some point, we're going to get a much larger code book for vision tokens, but I think we get there eventually. Okay. A core weakness of our tokenizer is in reconstructing images with a large amount of text. So when you're taking 512 by 512 images and turning it into 1024 discrete tokens, that's probably not high enough resolution to get tiny text. So like, for example, right here in this image of a chameleon, if you were to tokenize this and turn it into 1024 discrete tokens, you might garble some of this text, right? You just might lose the resolution required to like be able to understand this text. So we've seen this before for most vision language models. If you have very tiny text, it has a hard time reading that or tokenizing that. Okay. Boom, boom, boom. Maybe let's cut a little bit into this one here. So we're going to look at the Idefix paper a little bit. Question from Yang. Are these conclusions based on a well-trained model? I don't really know what you mean. I think that, yeah, they trained a model and then they're talking about it in their paper, but I don't know what well-trained means. Okay. Hugging Face, training their own vision language model. And in this paper, this is kind of like a best practices kind of situation. So basically over the course of the paper, they kind of show all these different findings that they learned whenever they were trying to train this. So Idefix 2 is an 8 billion parameter vision language model, which achieves state-of-the-art within its size category. So state-of-the-art within its size category, right? So one way that you can get state-of-the-art without actually getting state-of-the-art is restraining it to within the size. So if you can create the best tiny model, you can say, hey, this is the best model, asterisk, for tiny models, right? So a little bit of cheating there, right? Because this is actually state-of-the-art, right? Because it's matching GPT-4V. This is just state-of-the-art within the category of small little models. Okay, maybe one extra point here. Where does this name come from? Idefix, right? So this is because Hugging Face is French, right? So in France, there's a very popular comic book series called Asterix. This is Asterix. This guy here is called Obélix, Astérix, Obélix, and then their little dog is called Idefix, right? So Idefix is the name of the little dog of this character Obélix. So that's where that comes from. And there's a bunch of other references to this as well. So later on, they actually release the data set that this was trained on, and it's called the Cauldron. So that actually also comes from this comic book series. And in this comic book series, these are French Gaulois, which is like Celtic people. And they fight the Romans. And one of the kind of things that they do is they like drink from this cauldron of like superpower potion. So that's why the data set is called the Cauldron, and the name of the model is called Idefix. So that's kind of a little bit of a background for those of you that aren't aware of French cultural references. Okay. Many disparate design choices are not often justified experimentally. Okay, of course, right, as we were saying, this VLM, Hugging Face's VLM, which kind of represents what people have been doing up until now, is kind of really just gluing together a pre-trained vision backbone and a pre-trained language backbone, initializing new parameters to connect the two modalities. And the new parameters are basically these here, this kind of projection or adapter, which just changes what's coming out of your vision encoder into the type of tokens that need to be consumed by the language model. The input sequence of the language model is thus the concatenation of visual tokens and text tokens. So the green ones are the visual tokens, the red ones are the text tokens. Visual tokens can be optionally pooled into a shorter sequence, providing more compute efficiency. So pooling, right? And we're going to look at that here. So one of the things that they compare here is what type of pooling to use. So average pooling was found to deteriorate performance. So what is average pooling? Let's look at that. Average pooling is a technique where you have this here. Let's say this represents some image, right? This is some feature map for some image. Use a 4x4 matrix of images, right? So there's 16 total numbers here. Average pooling allows you to basically reduce that down to 4 numbers. So it's a lot easier to do stuff in your computer with 4 numbers than it is with 16 numbers. So pooling is a technique by which you kind of reduce the dimensionality of something by losing. It's like a lossy technique, right? So you're basically saying, okay, I'm taking the average of these numbers and doing that. So the problem with that is that you lose information, right? So maybe there was information in the 7 and the 2 that you could have used to make a better output. And by pooling it like this with a naive type of average pooling, you're losing some of that precision. So instead of average pooling, people are now using a little bit more fancy stuff, such as here a trainable type of pooling, which is called the perceiver resampler. Okay, so basically some kind of pooling that has a little bit of a learned parameters in there, and this learned pooling is effective. And so now people are using learned pooling, right, in order to reduce the size of what comes out of the vision encoder into the tokens that you then feed into the LLM. So the whole point of pooling is to basically reduce the amount of visual tokens, significantly improving compute efficiency at training and inference while improving the performance on downstream tasks. Okay. Exploring the space. Let's see. Okay, are all pre-trained backbones equivalent for vision language models? The greatest improvement in performance on vision language benchmarks come from changing the language model to a better one. Okay, so when you're doing this type of gluing vision language model, where you're gluing a vision encoder to a language model, the most important thing is that this language model here, which has been pre-trained, is very strong, right? You also want the vision encoder to be pretty strong, but what they discovered is that if you switch out this language model from a Llama 1.7b to a Mistral 7b, you're going to get a 5% improvement in score. So the most important thing when you're doing this kind of gluing approach is to make this language model big. But you don't need to give a shit about that if you're training them from scratch. So you don't have that problem here because you're not using a pre-trained model. Let's look at the pre-training for the Chameleon model. Okay, the Chameleon model is pre-trained in two separate stages. In the first stage, you use a data mixture consisting of the following very large data sets. So you have a combination of the pre-training data used to train Llama 2, so 2.9 trillion tokens of text. Then you also have text image, which is publicly available data sources and licensed data. A little bit, they're not telling you exactly what this is, but publicly available data is kind of like a secret way to say YouTube. So this is what the OpenAI, I don't know what she is, but the Mira Murati, whenever she was asked, like, what is GPT-4v trained on? And she said, publicly available data. Publicly available data is kind of like a euphemism for, like, we scraped YouTube and we scraped Reddit and we scraped all these other sites that are available. Like, you as a human can go on YouTube and watch any video you want. But does that really mean that you can just scrape all of YouTube and train on it? I don't know. So it's a little bit nebulous right now what people are training on, but you know, the AI race is heating up. People need to perform, so they're just throwing caution out of the wind, just saying, hey, fuck it, let's scrape YouTube and train on it. Okay, so over 1.5 trillion text image tokens. So that's in addition to the 2.9 trillion text-only tokens. And then text image interleaves, 400 billion tokens of interleaved text and images. So this is where you have maybe like a blog post or like a Wikipedia page where you have some text, some image, some text, some image, and the kind of proportion of text to image is like kind of random. Where the image is in relation to the text is also random. You want it to be kind of random, right? You don't want to have all your data have image, text, image, text, image, text. You want it to be interleaved in such a way that you can kind of equally output text or images. Okay, so that's going to be the first pre-training stage, and then you're going to have a secondary pre-training stage where you kind of start mixing in these higher quality data sets. And here when they say lower the weight of the first stage data by 50%, what they're talking about is that when you have these multi-stage training pipelines, you don't want to just hard switch, right? You don't want to have a data set for the first stage and a completely separate data set for the second stage, because then you'll have what's known as catastrophic forgetting, where the model will just kind of forget what it learned at the beginning because now it's being fed entirely new data. So usually the way that you want to do this is you want to kind of weave the data sets a little bit together, right? So initially you're training on this first data set, and then when you train on this second data set, it's not like you train on an entirely new data set. You start kind of like weaving in different data. So you still have a little bit of the data that you trained on initially, but you're weighing that data less. So it's like basically the gradient that results from a batch of data in this second stage is mostly coming from this higher quality data set, but you still have a little bit of gradient coming in from the original data set, just so you don't forget that original information that you learned. Okay. Is there something else I wanted to mention here? No, I think this is mostly it. Let's go back to the paper here. Okay. Blah, blah, blah. How does the fully autoregressive architecture compare to the cross-attention architecture? Do I want to talk about this? No, I think I'll mention this later. Okay, is there anything else here? Splitting an image into sub-images. That's not super important either. Obelix, here's the name of this guy here. Obelix is an open web scale dataset. Interleaved text documents, image text documents are the biggest driving factor in increasing performance on visual question answering VQA tasks. Okay. And you actually have a similar thing here. A large proportion of mistakes of the state-of-the-art VLMs stem from their failure to accurately extract text in images and documents, which is exactly what they were saying here. So kind of a similar find here, that because your image tokenizers are kind of lossy, right, where they're taking an already kind of small image and discretizing it into these tokens, which are inside a relatively small code book size, we're still not at the point where we can OCR like a picture of like an extremely tiny text type of thing. So both Hugging Face's Idifix and this Chameleon one have problems with tiny OCR text. Word tokens are a piece of word, but how would an image token look like? Can I imagine it like 10 pixels that represents the... Yeah, so when you're tokenizing an image, you are going to basically cut it into these patches, and then those patches are going to be encoded into some feature vector, right? So it's basically the same as text, where you're taking a sentence and you're chunking it into these little pieces of words, and then turning them eventually into feature vectors, little vectors that at that point you kind of lose what it even means, right? It's just a vector of numbers. So yeah, it's similar to text in that you're chunking it into pieces. So you can imagine taking this Chameleon and just cutting it into a grid of 14 by 14, and then just one little square would be what you turn into an image token. Okay. All right, we keep going here. Let's look at the architecture. So RMS norm, pretty standard. Swig loop, pretty standard. Rotary position embeddings, pretty standard. But one thing that they mention here is that because we share all the weights of the model across modalities, each modality will try to compete with the other. This is called the logit drift problem. Okay, so they're training this thing from scratch, right? This is now being done from scratch, and they're training kind of end-to-end, and they're fusing the modalities much earlier, right? So you're getting this interleaved stuff. This gives you benefits, right? It gives you the benefit of probably stronger performance because you're training this from scratch, fusing at the early, but now you're going to start to have new problems. And this new problem that they ran into when trying to train this is that your modalities are kind of competing with each other, right? If you're going to be outputting interleaved text and images, if it's easier to predict images, then the model's going to want to predict images, right? Because the model wants to basically predict accurately. So you're going to have to do some fancy engineering stuff here to make sure that you don't prefer one modality over the other, right? And that's kind of what they talk about here, where it was necessary to introduce dropout after the attention and the feed-forward layers in addition to the QK norm. This is the query key norm. So they normalize the queries and the keys. So you can see here that in Llama 2, you take your input X, you normalize it, and then you put it through the attention mechanism. Here, they're doing it, they actually moved it back to after. So now you take your input X, you feed it into the attention, and then you do this attention normalization. Okay, so they have to mess with the architecture a little bit and massage it because you're introducing new problems now by doing this end-to-end multimodality from the start. But that's okay. You know, we live and we learn, and eventually we'll get better and better. Optimization. They use the AtomW optimizer with here are the beta parameters. The one interesting thing I thought about this here is not too long ago, this guy here who works at Meta released this schedule-free AtomW optimizer. So there was a bunch of activity about this of like, holy shit, we figured out a new Atom optimizer that is schedule-free, no other tricks, it works better than all the other ones. Like, look at this, holy shit, we're going to all be using that. They don't use that here. So what does that mean? Okay, so either that means that this was basically a bunch of hype bullshit and like it doesn't actually work in practice, or there's like communication mishap or something like that. I don't know, but I just thought that was kind of interesting how like even though this person at Meta, like it seemed like Meta had discovered a new type of optimizer that's better than all the other ones, they're still kind of using the classic Atom W with different types of scheduling. So I don't know what happened there. Chameleon 7B was trained with a global batch size of 2 to the 23 tokens and a global batch size of 3 to the 22 12 million tokens. So these are monstrous batch sizes, right? And if you actually go later in the paper, they tell you what this is trained on. This is trained on Meta's research supercluster, which is based on NVIDIA A100s. And there's over 3,000 GPUs in this NVIDIA A100 research cluster, which is why this global batch size is absolutely monstrous, right? So when you're looking at Hugging Face here, making this VLM, using pre-trained vision encoder and a pre-trained LLM and just kind of gluing it together, they're not doing that because they're stupid, right? It's like these people are not stupid. If they could do this, if they could do it the Facebook way of end-to-end, they would do it the Facebook way. The problem is that there's only like 2 or 3 companies in the world that can do this type of like training from scratch. And, you know, like think about how much 3,000 GPUs over 4 million GPU hours, they're the only ones that can do this. So there's certain parts of model space and model architecture space that are only possible to explore if you have a massive budget, right? Like everybody else, like the open source community, we're kind of limited. We can only explore kind of parts of model architecture and model space that we can reasonably do on a small budget. So that's why we're starting to see kind of this bifurcation where the people who don't have huge budgets have to come up with all these tricks where they use a pre-trained vision encoder, they use a pre-trained LLM, versus the people like Meta, they can just train these things from scratch. So hopefully they release this Chameleon model and they open source it so that we can now start building on top of it. But if they don't, this might be no good for the open source community, right? Because these are the models of the future. These VLMs have kind of hit a ceiling, right? These type of VLMs where you're gluing them together, there's a ceiling to that. And I think the only way past that ceiling is training from scratch like Facebook did here. Okay. Let's look at this. Here's a little bit more information on the data. So the text data comes from basically Llama 2. It's the same data as that. The code data comes from Code Llama. SFT means supervised fine-tuning. So it's basically like the very last. So you see here how in the pre-training they were talking about using a higher quality data set. So in pre-training, you're using, I don't want to say noisy because all of these data sets are filtered to some degree, right? You have kind of data cleaning and data filtering happening even for these big data sets. But in pre-training, first stage, the data is kind of more noisy than in the second stage. It's higher quality. And then by the time you get to the supervised fine-tuning stage, this is like your cleanest possible data sets, right? So for text, for code, for image generation, they curate highly aesthetic images by applying and filtering each image. For the visual chat and interleaved text and image kind of chat, they also use very high-quality data collection from third-party vendors. So they got probably Scale AI, if I had to guess, sitting there, basically creating these extremely high quality data sets, which are the last ones that you train on in the supervised fine-tuning stage. And of course, they got the safety data. Safety data is a collection of prompts that can potentially provoke the model to produce unsafe content and match them with a refusal prompt, such as I can't help with that. So why do your models say, I can't help with that? Because a human at one point typed that into a keyboard and said, I can't help with that. So that's where that's coming from. Some human chose this particular set of tokens. Collecting mixed modal prompts is of particular importance since it addresses potential multimodal attack vectors which are outside the distribution of text only and text-to-image safety tuning benchmarks. Okay, so now they're introducing a new type of modality, right? You're doing this interleaved stuff. So now all of your safety type data sets can't be just text only or image text to text. They now have to be image and text into image and text. So new fine-tuning data sets required for this type of training. All right. Does pretty good, blah, blah, blah. I think it's now a single forward pass has 8 million tokens. No. So here, when they're saying a global batch size of 8 million tokens, there's a lot of models that are all being fed different parts of that global batch, right? So there's, when you're training these types of systems on 3,000 GPUs, you're doing what's called model parallelism and data parallelism. Model parallelism is when the model isn't on one GPU, it's being spread over a bunch of GPUs. And data parallelism is that you're not giving the same piece of data to every single GPU, you're giving different slices of that data, right? So when you have this global batch size of 8 million tokens, that's not one batch that's going into one GPU that has the one model in it, right? It's more like over these 3,000 GPUs, you have little slices of the model and they're being fed little slices of the data. All of that gets chunked through, you get the gradient, you push the gradient back, and it's usually not even just that. Usually you're doing some kind of exponential average of all the weights, and then that's kind of your one step. And the only way that you can do that is with these, for example, networking stacks. So these research superclusters, they're not just a bunch of A100s, right? So it's not like if Hugging Face just went on Amazon AWS and got the same 3,000 A100s, they would be able to do this. They couldn't actually do this. The only way that you can do this is when all of your GPUs are all connected via these very advanced kind of like networking infrastructure here called the quantum InfiniBand that allows them to communicate a lot, right? So if you're using this kind of data parallelism and model parallelism, there's going to be a lot of communication during training between the different GPUs, right? And that's only possible when you have this networking infrastructure. And that's another kind of separation that we're seeing, right? Where you can't access that through cloud providers. Usually, if you want this type of networking performance to do this type of large training, you need to basically buy the whole data center, right? So NVIDIA isn't even selling individual GPUs anymore. They're selling like the entire data center, right? So that's how they can do this. See if there's any question. Hasn't this architecture been obvious since VQGAN? Why only now? These companies are doing this. This is so old. Kind of. Okay, but I'm going to use that question as a launching point because I think there's an even cooler paper that I want to show you guys. And I want to show you guys this one. This is the Google multimodal paper, right? And why is this one cooler? This one is cooler because even though these guys call themselves mixed modal and multimodal, they're not. There's just two modalities here, right? There's just images and text. But this one is images in the form of video, audio, and text. Okay, so now this is actually more what we're talking about when we're talking about GPT-4o and Google's Astra, which they announced this week, right? That's beyond just a vision language model or something that just consumes images and text and outputs text, or something that consumes images and text and outputs images and text. This is something that is consuming audio as well. So this is, you're talking to the model, right? How are they doing this? So there's a lot of really cool tricks. This paper is very dense, but I'm going to try to focus on the important points here. Video and audio are obtained at a much higher rate than text and are roughly aligned in time. And that's the key part here. Roughly aligned in time is that audio, especially when you're taking it from video, there's a lot stronger relationship there in terms of the timing, right? The audio is kind of like corresponds to a very specific piece of that video. We decouple the multimodal modeling, dividing it into separate autoregressive models. We partition the video and audio sequences into consecutive snippets, right? So you take the video and you turn it into these chunks. So you see that the whole video is being turned into these chunks. You have a little bit of video and you have a little bit of audio. You have a little bit of video, you have a little bit of audio, right? So it's kind of like tokenization, but for audio video, right? So the same way that here you're turning a image into a sequence of text token or sequence of image tokens. In this one, they want to do the same thing, right? They want to turn this raw modality of video and audio into a sequence of things to feed it into a transformer. So they're going to use this little combiner, which is going to encode the video and the audio. So this is kind of similar to this design here, right? It's actually very similar to what I'm calling the old school vision language models, where you encode the vision and then you project it into image tokens that then get fed into the LLM. That's actually kind of similar to what's happening here, except now you're also encoding audio. So you're encoding the audio and the vision. They actually do this at the same time, and then they're going to turn that into these tokens, and then that's what they're going to feed into here. So it's still this kind of two-part approach. So I think that what GPT-4o is it's basically this, but end-to-end. So it's from scratch end-to-end with audio. Okay. This combiner mechanism models the audio vision information jointly, producing compact but expressive representation. So here's this little combiner piece that is basically just kind of like a projector. It's taking the video and the audio and turning it into these tokens. This is state-of-the-art on multiple well-established multimodal benchmarks. Everything is state-of-the-art, but at the same time, nothing is state-of-the-art. Video and text have different sampling rates. Video and audio are naturally co-occurring and appear almost synchronously. This co-occurrence in time can contribute to the joint learning and serve as a rich self-supervisory learning signal. So this self-supervising learning signal, what they mean by that is that they're actually going to be training these video encoder and audio encoders kind of in tandem with this model, right? So rather than using some pre-trained video encoder and some pre-trained audio encoder, they're going to be training the video and the audio encoder by trying to basically predict, using kind of like a masked reconstruction loss, by trying to predict what comes out of this, which they're going to call hidden states. Okay, cross-attention weights coordinate the learning between these components. This decoupling allows for better parameter distribution within the model. So maybe this is a place where we can talk about the point that the OpenAI paper was, or not OpenAI, the Hugging Face paper. So one of the lessons that they learned in the Hugging Face paper is comparing a fully autoregressive architecture compared to a cross-attention architecture. So I have here an image of the original attention is all you need figure. So this is from the original Transformer paper. And I'm using this to explain the difference between cross-attention and self-attention. So this little orange block here, this is the attention head, right? A multi-head attention. And here you can see it's doing self-attention. So the queries, the keys, and the values are all coming from the previous layer. So the transformer here is just paying attention to kind of the outputs of its previous layer. And that's called self-attention. Cross-attention is when the queries, the keys, and the values are not all coming from the previous layer. Some of them are coming from some other thing, right? So in the original Transformer paper, this was basically a sentence in one language, and it was trying to create a sentence in another language. But cross-attention is, you see it everywhere, right? So in diffusion models that are conditioned on text, you have cross-attention there. But the problem with this type of cross-attention is that, as they say here, the more frequently the cross-attention blocks are interleaved with the language model layers, and the higher the vision language performance, but cross-attention architecture is worse when we add degrees of liberty. So basically, the problem with this cross-attention is that it's more, it's harder to train because it uses more compute, and it's going to make inference harder because it also uses more compute, right? So it just makes it more complicated, more compute. You don't want to necessarily use that. So if you're Hugging Face and you're trying to do things relatively cheap, getting rid of this cross-attention architecture is more efficient and better. But if you're Google, right, and you can train these things from scratch, then cross-attention is going to help because you're allowing kind of information to flow, right? So cross-attention is good because it allows information to flow from this thing into this thing. So here, they want information to flow from the audio and the images into the kind of more texty type of stuff. So that's why they are saying cross-attention is good, versus if you go in this paper, they're saying cross-attention is bad. Okay. So a lot of these architecture tricks, you might see it in one paper where they say, hey, this thing is good, and then in a different paper, hey, this thing is bad. So don't read too much into like these kind of alchemical conclusions that people come up with in these papers, because usually that's just constrained to a specific paper. Okay. All right. let's go into this. Related work. Some architectures instead extract full video signals before feeding them to the model. Another option is attack a reprojection or retokenization layer, right? So that's exactly what we're doing here, right? This is a projection or retokenization layer right here. So they're saying, okay, we're not going to do that. What we're going to do is video and audio information is sequential. We are going to have an input video sequence of n frames and an audio wave signal of m time steps. So you have your audio signal here and you have your input video here, and you're going to be encoding these. And actually the way that they encode these is quite interesting here. They're going to be representing the audio as a spectrogram. Okay, so this is something that people have been doing for a while, but this is a spectrogram of audio, right? So audio is a wave, and you can decompose that wave using your kind of just standard like Fourier transform type stuff, right? So this is audio broken down into different frequencies, right? So why are we doing this, right? Because this is now an image, right? So through this type of spectrogram, you've turned audio into an image. And if you turn audio into an image, then the VIT backbone, the vision transformer that you're using to encode the video, which is a bunch of images, can also be used to encode the audio, reusing the visual component. So this is a really nice little trick that Google did here, right? Where if you were going to do audio and images together, it would be kind of shitty if you had an audio and then the audio went through an audio encoder and then you had to do this here, right? And then you had a vision and then you had a vision encoder, right? Having a separate vision and audio encoder, that would be kind of shitty. But if you can turn the audio into an image, now you can use the same encoder to encode them, right? So now you're reusing that vision transformer to both consume the vision and encode it and consume the audio and encode it. The problem with that is now you can't just use some pre-trained vision encoder. You're gonna have to train this thing from scratch, but that's totally fine if you're Google because you got the money to do that. Okay, so they're training a new type of encoder that is consuming these audio video chunks and giving you that, which is a pretty nice little feature there. Okay. The features for each modality are roughly time aligned. The extract sparse 3D tubes. So actually the vision encoder is consuming these tubes. So you see this tube here. So you have each of these blue squares here is that frame of an image. So a video is just a frame of images. And these tubes are basically correspond to a specific local region in space and then a specific region in time, right? So this green square here represents kind of a large spatial part of the image, but then a short sequential part. So like it's only a certain amount of the frames, but more space. And then you have some tubes here, such as this pink tube, that have the entire sequence. So they have a large time receptive field, but a very small spatial receptive field, right? So you're kind of playing with the receptive field of the different encoder here. So you have the ability to encode features that represent the whole sequence versus features that represent kind of a more spatial information. Okay. Blah, 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 blah. What else we got here? 25 frames per second, combining time-aligned modal latent features into a smaller set of shared latent features. So now you've basically created these features, and then you can train these encoders using reconstruction loss with random masking, right? So that's kind of what they were saying here, that you can train these from scratch by trying to predict the output, right? So you're kind of masking some of these and then using that to reconstruct. And that's how they train these. The combiner is just a transformer. Okay, and now we're going to get to this. But before that, let me go back to here. All right. So in the Facebook paper, right, they're doing this early fusion and they're outputting interleaved text and images, right? So as we said before, this is going to introduce a bunch of new problems. And some of these new problems, I think, are kind of interesting to look at. So given that our decoding formulation changes depending on whether the model is generating images or text at a particular step, tokens must be inspected at each step. Okay, so you have different tokenizers, right? You have a tokenizer for the images, you have a tokenizer for the text, which means that when you're decoding or basically producing tokens in inference, right? When you're actually running this model and outputting tokens, you have some conditional flow there, right? And that conditional flow, think of it just like an if statement. If the output is image tokens, then you need to use this, and then you need to put it into a little image buffer and then eventually show that image, versus if you're outputting text tokens, you need to feed it into this, right? That type of conditional flow is very annoying to implement efficiently. So that's a new extra thing that you have to deal with, right? That you don't know whether the next token is going to be an image token or a text token at inference time, which makes it kind of annoying to perform inference. To facilitate exclusive generation for a particular modality, tokens that do not fall in a particular modality space must be masked and ignored when detokenizing. Okay, so that's a problem, right? Let's imagine you're here and you're outputting this, right? You're outputting this interleaved text and image. Your model's going to output text token, text token, text token, text token, text token, image token, image token, image token, image token. But what if suddenly it was like, okay, actually, I kind of want to output a text token right now. You actually want to block that. You don't want, because you want it to finish the image before it does any more text, right? So we're seeing a little bit of a complexity here coming from the fact that you need to be much more restrictive to the model and know, okay, you're outputting image tokens. Okay, you need to finish this image before you can output any text tokens. Unlike text token generation, which is inherently variable length, token-based image generation produces fixed size blocks of tokens corresponding to an image. That's another problem too, right? So let's say you're at the very end of your context length, right? And you want to and you end halfway through this image. You can't just give the user half an image, right? So you have to do the rest of the image. So kind of interesting, right? These are things we haven't really had to think about, but if we're going to be moving into this multimodal world where you're outputting mixed tokens, you're going to have to deal with these issues now of like, hey, you might be outputting image tokens, then you can't pause halfway through, right? And these guys don't. You're going to have an even more similar problem here with the video and the audio, right? Where if you're outputting video and outputting audio, which we're going to eventually get to, right? Even GPT-4o isn't doing that. GPT-4o outputs audio, but it doesn't output video. So we're kind of approaching this from different angles, right? These guys are outputting audio or images and text. These guys are just outputting, I think, just text and inputting video and audio. So we're very close. I think we're just less than a year away from video, audio, text going in, interleaved, and then outputting video, audio, text, interleaved, right? So like that's really the endpoint we want to get to. We want to get to a point where we're outputting interleaved multimodal, and that thing is not going to be some piecewise bullshit like we're seeing here, right? Where you have different parts and then you're gluing them together. It's going to be like this. It's going to be an end-to-end trained from scratch early fusion multimodal with chunked audio and video. Dude, all right, you guys are going wild on the chat here. I thought he might be French as he was good with maths. I technically have French citizenship, BTW. I'm not like a real French boy, but je suis français. Un peu français. Can't we just wrap text and image and text and image so you won't be generating other modalities until the end of the contemporary modality? Yeah, they do that. So Pratyush is bringing up a good point here that whenever you're tokenizing like this, usually you have specific tokens that denote the beginning of an image and the end of an image. So you're letting the model know, okay, start image token. Okay, the next X tokens are going to represent an image. And then once you do the end image token, then you can change the modality. But it seems like they still have issues with that. So they don't really explain it 100%, but it seems to me like there's probably some failure cases where you're trying to output an image and then it starts outputting text halfway through the image. That would be my guess, but I don't know. Okay. All right, so we were looking at the combiner. Now let's talk about this, because this is buried inside this paper, right? So when you look at this paper, you're like, oh, multimodal autoregressive model. All right, cool. So they're consuming audio and text. Oh, okay, cool. They have a little encoder for that. Oh, okay, awesome, cool. And it outputs text. All right, cool story. That's not the best part about this paper. The best part about this paper is buried underneath, right? So you go all the way, page 2, 3, 4, you get to page 5, and now suddenly they talk about a token Turing machine. Whoa, what is that? A token Turing machine is a recurrent sequential model with transformers and token-based operations. It maintains an external memory. Whoa, okay. A memory? Given inputs U of t, it first reads features from the input features as well as the memory. Such features are then passed to the processor, which is also a transformer, generating a set of intermediate output features. These intermediate outputs are then used to update the memory and produce the final output. Okay. So wait a second. Now your input features are being put into some kind of memory, and that memory is being used in addition to the input features to produce your output. Okay, so you see here, and it's kind of like way in the corner here. You can't even see it. Let's zoom in. So, let's get to that. Boom. You see that? This is what you think this paper would be, right? You would think that this paper is just this, right? Oh, you're just consuming audio vision tokens and you're outputting text tokens. But no, it's actually a Turing machine, right? A Turing machine is, think of it like a computer, right? It's actually taking in the audio vision information, processing that, and sometimes it puts it into this memory, and then sometimes it doesn't. And then this is what outputs that. And this is a very important point because this is what's happening in GPT-4o. If you remember in one of the demos, the demo that Greg Brockman gave, and I think Greg, the demos are picked, right? So like when you're demoing something and you're Greg and you understand the system all the way from to the lowest level, right? You want to show off the parts that are really impressive. And the one part that's really impressive here is he's like listening to the thing, it's talking, this person comes, he like shoos her away. And then after she leaves, he asks the model. So he waits until she leaves, and then he asks the model, did anything happen? And the model's like, yeah, somebody came up behind you and did bunny ears. But the impressive part about that is that it happens after. So what that tells me is that there's a memory, is that the model that GPT-4o, it's not GPT-4o, I think it's like the vision, GPT-4o, vision, whatever the fuck they want to call it, the one that they were showing here that is multimodal, it has a memory. So it's like this. It's a Turing machine. They have this implemented. They have a memory storage, which is storing information and then being used to retrieve. And so it's kind of like a little built-in RAG, if you want to think of it that way, right? So that's a very important part here that I think people might have missed, right? Where it's not just outputting based on what it sees right now. It has like this kind of memory that it's storing. So memory or attention span. Yeah, attention span is basically, an attention span is the size of this memory, right? So the size of that memory determines the attention span, right? And the benefit of that, the benefit of this type of memory is that it reduces the total time complexity of the token Turing machine to be constant with respect to t instead of O. So basically O of t instead of O t squared, right? So in traditional transformers, you're doing this self-attention, your memory is, or your computation is based on the fact that you have to consume the entire sequence every time. So if you have twice as many tokens, it's going to take 4 times as much time, right? Because it's twice squared. But when you have an external memory like this, you're only ever going to consume the size of the memory, right? So because the memory is fixed, right? If you have 10 hours of video versus 1 hour of video, it's still the same size memory. So no matter what, the time complexity is always going to be O of t rather than O of t squared. And there's kind of like a self-awareness here that some of you might have kind of realized, because when I was reading this, the first thing that I thought of, I was like, wait a second, this is a fucking LSTM, right? Like you're talking about a memory, and they even use the word here, the hidden state H. So they have some combined latent representation H. I'm like, wait a second, that's a fucking LSTM. You have some memory which is fixed, which means that this is O of t, and then you have these forget gates, these input gates, these memories, right? So you're basically adding shit to the memory, removing shit from the memory, and then using that to basically then predict the next thing. So what this TTM is, this token Turing machine, is effectively just an LSTM, but rather than an LSTM, which is doing this at a kind of like a microscopic level, right? It has like, this is literally learnable forget gates, learnable input gates. You're implementing these in kind of as like neurons. In the case of this paper, you're implementing these as transformers, right? So the processor is just a transformer. The thing that removes things and adds things to the memory is a transformer. The things that outputs is a transformer. So it's kind of like an LSTM, but you're replacing all these little pieces with models, right? So no matter what, we always end up at LSTMs and RNNs. Okay. How do they train this? So there's a couple different losses that they use to train this model. It's pretty much what you would expect. They have standard cross-entropy loss between the target and the output text sequences. So in this case, it's outputting text. So you basically have some input and some output, and you're just using standard kind of like supervised learning to say, okay, this is the token that you should have predicted. This is the token that you did predict. All right, let's push a gradient based on that. But they also have this modality reconstruction, this reconstruction loss, which is basically you mask some of these audio visual tokens, and you use that to push a reconstruction loss into these encoders, right? Because they have to train this encoder from scratch because it's new, right? You're basically using a spectrogram and like video chunks, and you have this 3D tube shit going on. So in order to train these encoders, you have to have some kind of reconstruction loss as well. Okay. Let's go into a little bit of details of the model here. So this is a very tiny model, right? This is Mirasol 3B. It's only a 3B model, so very tiny. Let's go down to here. Down to here. 3B model, half of the parameters are for the audio plus video autoregressive model, which actually, think about that, right? So half of the parameters are for the audio video autoregressive model. So half of the parameters are here. They're in this combiner video encoder audio encoder, right? So half of your parameters are here, half of your parameters are here. That doesn't seem as strong as this, right? Because in this, 100% of the parameters are here. So I actually like this early fusion better than this, which is kind of like a late fusion, right? So I think that where we're going to end up is kind of like a combination of these. I think we're going to have early fusion, audio, video, and text into one giant end-to-end autoregressive model. Okay. What else we got here? Apply random masking, dropout regularization. Model is pre-trained on video text pairs over 3 million samples. So this is pretty small peanuts, right? And this is not Astra, right? So like this is not the Astra, but if these people are working on this, the people working on Astra are kind of learning from this. So like, I think the way that Google publishes stuff, it's like they don't publish the secret sauce, but they'll publish like a kind of a version of the secret sauce that is kind of like small and kind of related, right? So it's like, it's not a coincidence that this paper, Mirasol 3B, which is doing this kind of combined video audio encoding, is coming out when they demo the Astra model, right? This is not the Astra, but the Astra is basically the same thing as GPT-4o. So I don't think it's a coincidence, and I think we can use this to kind of guess what the Astra model is, right? So you can think of this basically just like a tiny, shitty open version of the Astra, but a lot of these same tricks are probably being used in the more production version of the model that is closed. Method outperforms all prior methods, but not really. Across all datasets, we perform state-of-the-art with large margins, but not really. Processing the video chunks autoregressively in time is more advantageous than learning from the full video at once. A little bit of causal masking there, basically. But yeah, that's Mirasol 3B. All right, let's look at some of these numbers for here. Some of the performance. These guys mostly compared using the human, which I think is the better way to compare, right? So like partial fulfills, does not fulfill, fulfills. Okay, so GPT-4v doesn't always tell you what you want. And they couldn't even compare these things directly, right? Because think about it. While these models can take mixed modal prompts as inputs, their responses are text only. So GPT-4v and Google Gemini Pro, they can consume interleaved text and images, but they can only output text. So how do you compare GPT-4v to Chameleon? Well, the way that you do it is you augment GPT-4v with images. So you tell GPT-4v, if the question requires an image to be generated, generate an image caption and then enclose the caption in a pair. We use the OpenAI DALL-E 3 to generate the images. Okay, so to even compare Chameleon to GPT-4v, they basically have to use GPT-4v in combination with DALL-E 3 and Gemini Pro in combination with, I don't know what the Google generation one is called, but that's kind of cool, right? That this model is so advanced that they can't even, there's no benchmarks to compare it to, right? They have to like literally kind of glue together multiple products from the competitors in order to compare, because the competitors can't do this type of interleaved output, right? The competitors only do text-only output. Even this one here, this is only text-only output. So yeah, this Google paper, definitely more advanced in the fact that it's consuming audio-visual, but it's less advanced because it's outputting text only. This one here, the Facebook one, it's outputting text and images, and it's inputting text and image. So it doesn't have audio, so it's less advanced that way. But I think if you overlap these papers as a Venn diagram, I think that's pretty much what GPT-4o is, right? It's a basically interleaved end-to-end with an external memory, right? And that external memory part is key because that's how you're going to get... so they built in RAG, effectively, but like probably has a bunch of secret sauce tricks to make sure that it's fast. Okay. Question from Explorers. Are we getting into models being stateless to stateful? Inference memory requirements change a lot. Yeah. That is part of the problem here, right? Is that right now, when you're performing inference with something like GPT-4, it's kind of stateless, right? You're just talking to this model, which is loaded on the GPU, and the information in your prompt is just directly being fed to the GPU, and then it outputs that, right? So in terms of like the compute that you need for inference, that's relatively straightforward. But when you're going to start having these more complicated type of inferences where you need to have this memory, right? Where are you putting that memory? Is that in the RAM for the GPU that's consuming your stuff? Is that memory sitting in some database somewhere and you have to wait for it to send it back? Like, do you have additional things in your memory, such as previous interactions that you had? So this type of inference where you have to be loading things in and out, kind of like a RAG, that's going to be much more complicated to implement in the actual data centers that are performing these inferences for you. So yeah, I don't envy the people that have to solve that problem, but they'll probably figure it out. Pratyush, question on the RAG you mentioned. Do you intuit that GPT-4o is creating visual tokens for KNN retrieval or text description of frames created and stored? So in the RAGs that you see implemented in open source, they will retrieve information from some database or table of information, usually based on some similarity metric, right? So they're using some similarity metric to find relevant pieces in your database and then pull those forward. That's slightly different from what's going on here, right? And here, it's more like an LSTM, right? It's more like it has some memory and then the model is kind of just directly putting shit in and out of that, right? So you're not doing RAG in the sense that you're like kind of like finding things, putting them in there, putting in the context, and then reading it. Like this thing is like it's closer to the actual model that's actually doing it. So like I think of it more like an LSTM than like kind of a RAG with an external database. But ultimately, you're going to want to have more external information, especially if you're going to have like previous sessions, right? So like the LSTM type of memory that I'm describing works well for this type of situation where it's just like 5 seconds later, right? Because that's like within that span. But imagine if you want to talk to this thing and you want it to remember something that you told it like 7 months ago, then you're not going to be able to do this type of like more like short attention span, like LSTM type memory. You're going to have to do kind of a more big boy RAG type thing where you have some cold storage data that you're pulling up from 7 months ago. Okay. Anything else here? Can't be that the context length is very big. ChatGPT uses memory updates and keep those references from future conversation. Yeah, there's a bunch of tricks that have come up over time to make the context length bigger, but you could still use those tricks, right? So like at the end of the day, you're turning audio and video into a bunch of tokens, right? So it's the same thing here. You're just turning audio and video and images into a bunch of tokens. So all the same tricks that you use to extend context length, right? Like long rope, flash attention, which is more of like a performance type of thing. You can still use those same exact tricks here, right? Because it's the same stuff. It's just all tokens. If it's all tokens, everything is the same. Memory in the pic can be thought of as a hidden state. Yeah, that's kind of what I'm getting at with my LLM analogy, is that this memory right here is very similar to this kind of hidden state and memory here, right? It's basically some brick of numbers that you're passing forward to the next thing. Okay. Is there anything here? The token Turing machine. Latent causal modeling. Text might not necessarily align, so here it is modeled by a separate autoregressive model devoted to text representations. Here's the cross attention. Is there anything else here? I feel like most of this doesn't really matter. I honestly, like, I don't even read these benchmarks anymore because it's like meaningless, you know, like these numbers are like based on some other previous thing. You don't really know like if they implemented it correctly. Like you don't even know if they're cheating. There's like zero shot, multi-shot. Like they don't even tell you that. So like the benchmarks are becoming increasingly meaningless to me. At this point, I'm more interested in the like qualitative improvements and differences in like what your model is actually doing. Right? So the open source world is still stuck in this like vision plus text, encode the vision into vision tokens. You're using pre-trained shit, and then you're using a pre-trained LLM. Meta is, okay, we're going to train it end-to-end, and we're going to interleave text and images, but we still haven't even touched audio. Google and OpenAI are now at the level where they're like, okay, we're consuming audio, vision, but we're still just outputting text, which is, I think in this case, they output the audio tokens as well. But we're very, very close, right? Because it's really not that much of a jump to, instead of outputting just audio tokens, output vision tokens too. So you can output video tokens, right? And if you can output video tokens, that means that we're very close to a version of GPT-4o where it's not just talking to you, but it's like literally a video of Scarlett Johansson there talking to you, right? So it's like literally a full audio visual representation in a 2D screen of an AI. And if you project that another 2 years forward, now it's going to be in a VR avatar, right? You're going to have a VR avatar that is literally being generated by an end-to-end autoregressive language model token, literally with tokens, right? And I think that's going to be where people's mind breaks, right? I think like a little audio assistant, I feel like the Overton window for that, like people are okay with that, right? Like we have voice assistants, we've had the Google Homes, the Alexas, the Siris. We're kind of comfortable with talking to something that's just talking to us with audio. But I don't think people are ready for seeing something that is like visually there, right? Or like you put on a VR headset and there's like literally a rendered, maybe it's Gaussian splats, but it's like a person talking to you and it's like moving and it's like blinking and it's opening its eyes, right? Like, and if you want to go into the world of robotics, right? Rather than outputting image tokens, it's outputting control tokens. So it's simultaneously outputting audio tokens, control tokens. So the robot itself is kind of running end to end. And that's where I think all of this is going, guys. I don't think it's going to be this. I don't think we're going to be doing separate vision encoders and then kind of like gluing them together like this. That's 2023, 2024 type of stuff. I think 2025, 2026, it's going to be more like this type of shit. End to end. What modalities do you want? What else? Your prompt is the conditioning to the model. Why the generate modalities in sequence? It should be parallel, no? Yeah, so Pratyush is saying, why are we generating these in a sequence rather than generating them at the same time? And the answer to that is it's a transformer. Unfortunately, a transformer is a sequence-to-sequence model. It can only output one token at a time. You can do, there's tricks, so there's things like speculative decoding, right, where you can decode more tokens than just one at a time. But this isn't like a classic algorithm where you can basically implement it in parallel, right? This is a model. You're like feeding a model with inputs and it's outputting things kind of one at a time. So maybe in the future there's like a way to run a model kind of in parallel, but you're still kind of just limited by the fact that this is a transformer, so it's going to just output one token at a time. GPT-4o showed that output can be 3D models. Yeah, I think that's eventually where we're going, where it's not like anytime I see a two-dimensional image, I feel like that's just we're still living in this like limited world, right? Where like cell phones and computers, all the things that we interact with now are two-dimensional, right? So we're generating two-dimensional images. We're consuming two-dimensional images. But eventually, once everybody has VR headsets, we're going to be 3D native rather than 2D native. So rather than these models outputting two-dimensional tokens, we're going to have the concept of like a Gaussian splat token, right? So it's not going to generate one Gaussian splat at a time because Gaussian splats are millions of splats, but there's going to be the same kind of idea of like tokenizing a 3D environment and then taking a sequence of tokens that represent 3D and then turning them into a 3D thing. So I think that's still a couple years away. I would say more like 3 years, 4 years, 5 years, but the basic recipe is there, right? Where if you can turn any modality into a sequence of tokens, you can not only consume that, but you can also output that and generate that sequence of tokens. And I think it's just a matter of time before we're consuming three-dimensional tokens and outputting three-dimensional tokens. Yeah, control tokens would also be a thing there. So you would have specific control tokens for a robot. Holodeck when? Soon. Soon, very soon. I can't see a world where we don't have this in 5 years. I think 1 year is like a little bit too aggressive, but 2 years, okay, maybe a little bit. 3 years? 3 years seems like a long time, you know? 3 years, 4 years, 5 years? Like 5 years, you got to have robots running end-to-end models at that point. You know what? Like when I started this paper, I thought it would take me forever, and that's why I was kind of blasting through it. But like, look at this. We're only an hour and a half in, and I've pretty much finished. This is like kind of everything I wanted to mention. Shall we do a summary? Give you guys back some time? Is the image tokenizer a VQ-VAE or a GAN? It's neither of those. A VQ-VAE is a VAE is a variational autoencoder, which is a way of creating basically representations for images. So it's in an autoencoder, you're taking an input, you're compressing it down with a bottleneck, and then you're compressing it back up to the input, right? You have an encoder decoder. And because those two images, when you feed it to the encoder and when it comes out the decoder, because those two images should be the same, you can effectively push a gradient and have this reconstruction loss, right? And then a vector quantized VAE is just that bottleneck is vectors that are within a specific codebook, right? But here, this is more being trained from scratch. So it's not like they trained a VQ VAE and then just plugged it in, right? That would be more like this. Like you could do this vision encoder here could be a VAE, an encoder coming from a VAE, but in here, there's no VAE going there. And then the GAN is a generative adversarial network. That's like also a similar concept where you're taking a thing and then compressing it and then making it big again and then comparing the output to the real one. Similar kind of concept, but that's not really what's happening here. A transformer could have multiple outputs as long as those aren't dependent on each other. So you can make it text and images at the same time. Yeah, I mean, you could kind of do that. So something. What you're describing is basically like you would have two different language models, right? You would have like a language model that outputs tokens, and then you have two different decoders. So you could have a decoder that outputs text and a decoder that outputs images. But there wouldn't really be a benefit to that because then you'd have these, like it's easier to just have it all be one model, even if it only generates one token at a time, rather than have like a model that is specifically outputting image tokens and a model that is specifically outputting text tokens, because then at some point you'd have to kind of wait, right? Like how do you interleave those? How do you create something like this, right? Because when you train in interleaved text and image and you output interleaved text and image, you know the model is saying, okay, now I'm finished with the text and now I'm going to output images and now I'm going to output, now I'm finished with the image and now I'm going to output text, right? So like, because you're outputting these things one by one, you know exactly when the sentences stop and when the images start, and when the images stop and when the sentences start. Versus like if you had separate heads that were decoding, you'd have to then solve this problem of like, okay, when should I insert this image and when should I stop the sentence? When we split the image into patches, we currently move from left to right and top to bottom, instead of we move from the center outward in a spiral. Yeah, so old kips, that is what happens. So when these images are turned into patches, usually those patches are literally just fed left to right and then top to down. And there's a bias there, right? There's kind of like an implicit bias that you're introducing by doing that. But a transformer has self-attention mechanism, and the self-attention mechanism is doing the attention between every single part of the input sequence and every single part of the input sequence. So whether you flipped the image tokens order, it wouldn't like matter as much. Sure, you still have the position encodings, but because you're feeding this into a transformer, it doesn't matter that much. On the other hand, with something like a LSTM or some of these vision mambas, right? We've read some papers on vision mambas. Those do have an inductive bias for the sequence that is much stronger than the transformer inductive bias. So in that case, you do need to be careful about the order. And that's why in these mamba papers, you usually see a couple different scan directions. So you'll see a scan direction that's left, right, top, down. Then you'll see one that's right, left, bottom, up. So you don't need to worry too much about the scan direction for a transformer, but for something like a recurrent model like a Mamba or an LSTM, the scan direction matters a lot more. How does the image tokenizer work? Question from Druba. The image tokenizer is here. VIT image encoder. This. What about this one? Okay, so you're taking your image, you're turning it into a bunch of little patches. You're feeding each of these little patches into a transformer with a little bit of position information. So you're kind of telling it this is the top left one, this is the bottom left one, and so on. And then that transformer is just eating it. It's just eating these tokens. It has no idea what the fuck it's doing, and then it just outputs a sequence of tokens. And those sequence of tokens are now representations as opposed to just patches, right? So the more after every single layer in this encoder, the representations are becoming more and more abstract, right? So kind of what they're trying to show you here is that initially the representations at the kind of lower level of these, at the lower layers of these transformer blocks are things like edges and colors and stuff like that. But then as you get higher and higher, they become more abstract. So by the time you get to 8,192 image tokens, it's like they're these kind of like abstract representations of all possible image tokens that it's seen in its training data. Hot take, make it only output images and use a different model to make it text. I mean, the problem, so here's my problem with this, JC, is that you guys are basically, your brains are ignoring the bitter lesson, right? Anytime you see this type of diagram, your human brain wants to like add more little arrows here. You want to add like, oh, well, what if we had a separate little model here that did this thing and then outputted this thing, and then I had a little regularization here that did this, and then I did this little image here. It's like your brain wants to break it down into pieces and add more little pieces, and like just, you want to over-engineer this, right? The human instinct is to over-engineer this, make it more complicated, add more little diagrams here. But what the bitter lesson tells us is that that's not actually what you want to do. You want to remove complexity. Remove complexity. The artificial superintelligence of the future is just going to be one end-to-end model that just consumes tokens, and that's it. And it outputs tokens, right? So it's like, instead of adding all this extra shit, such as a set, like multiple different heads for different modalities, adding a separate encoder, like just remove complexity and then make the data set bigger, make the, train it for longer and make the model bigger. And that's all you need. All you need is just bigger model, more data, train for longer, and then just remove the complexity, which is actually very pleasing, right? Because it would suck if we were kind of in the expert systems paradigm where you had to basically add complexity, add more little modules here that feed into other little modules in order to make this better, right? If that was the future, we're screwed, because engineering complexity becomes harder and harder and harder. But the way that AI and deep learning is moving, it's like you remove complexity to make things better rather than adding complexity to make things better. Okay. Did they mention how they handle position encodings with the multi-modalities? Yeah, they mentioned they use rotary position encodings. So right here, rotary position embeddings right here. But that's pretty standard. So I don't think they're doing a lot of innovation on the position embeddings. What are the main challenges faced when integrating different data modalities and multimodal models? Can it be resolved with the Mamba architecture? Not really. The Mamba architecture, like the architecture doesn't really matter that much, you know, like whether it's a Mamba or an LSTM or like any of these things, like it's not super important. There's not going to be like, it's not like the Mambas are going to suddenly fix all these issues that they have. Like you're going to have the same issues with the Mambas. Whenever Hupo talks about bigger models and simple architectures, I question my existence. Yeah, me too, man. I don't know where we're going. Okay. I'm going to sip this water, and I'm going to summarize this, ask your questions, and then we'll end it there. All right. So today we reviewed 3 different papers on multimodal models. All right. Multimodal models are all the rage right now because the 2 biggest players in the AI race, OpenAI and Google, released multimodal models, right? So OpenAI released GPT-4o, but a version of it that we haven't really gotten access to, which is this kind of like multimodal version. And then Google released Project Astra, which is basically the same thing, right? You can stream video and audio to the model, and the model outputs audio, right? Streams out audio. So we wanted to kind of figure out what is the current kind of state of the art? What's the landscape in multimodal models right now? So one thing that we looked at is the open source world, right? Hugging Face kind of represents the open source community. You don't have a ton of money. You can't be doing giant training runs. So whenever people build multimodal models in the open source world, usually they're building what are called VLMs, which are very basic multimodal models, right? They're only capable of consuming images and text, and then they output text, right? So it's only 2 modalities in, 1 modality out. And not only that, but these things are basically glued together in pieces, right? So Hugging Face is not training the vision encoder, and it's not training the LLM. It's basically just taking a pre-trained LLM and a pre-trained vision encoder and just kind of gluing them together and putting a little bit of extra layers in here just to make the glue work, and then that's pretty much it. Okay? Kind of performs okay, does well. Okay. Now, we have Meta. Meta has a bunch of money, right? Meta can waste money on 3,000 GPUs. So Meta can do the more ambitious version of multimodality, which is Chameleon. Chameleon is a mixed modal early fusion foundation model. So it's a model or a foundation model that consumes interleaved text and images and outputs interleaved text and images. So now we're talking about 2 modalities in and then 2 modalities out, right? And interleaved images and audio, or images and text. So the way that they do this is by training this from scratch in an end-to-end fashion on 10 trillion tokens on 3,000 GPUs, all hooked together with this massive NVIDIA quantum InfiniBand where they're pushing these giant global batch sizes of 8 million tokens. Okay. Pretty awesome stuff, right? They have a new tokenizer for the images. They have a new tokenizer for the text. It seems like it's still early days, right? The image tokenizer still feels like it could use a bigger vocabulary. They're still using a lot of the same trick or architecture of Llama 2, right? Swiglu, RMS Gnome, rotary position embedding. So we're still kind of early days, but this is, I feel like, where we're going, right? Multimodality in, multimodality out. And not only that, it's state of the art. State of the art for compared to GPT-4V and Gemini Pro, which were the current state of the arts for multimodal. But I don't think this stops here because there's one more piece that's missing, or actually 2 more pieces. And that's why we looked at this paper. So this Mirasol paper, this is coming from Google DeepMind. And in this paper, they consume 2 modalities, but really it could be 3, right? You could have text here as well. Video, audio, text, and then it outputs text. So in this case, 3 modalities in, 1 modality out. But now we're almost there, right? Because there's really only 3 modalities you care about: video, audio, and text. That's the only thing that's here. Video and audio in, audio out. So this is video, audio, text in, and then text out. So very, very close to what Astra and GPT-4o is, right? So they also kind of train these encoders from scratch. They do some awesome tricks like using a spectrogram, representing the audio as a spectrogram, which allows them to reuse the vision transformer backbone. But the other important part of this paper, which is kind of like an afterthought, and maybe the reason it's an afterthought is because they want it to be secret about it, is this token Turing machine. So the token Turing machine is basically recreating an LSTM or any kind of recurrent model like a Mamba that is keeping track of this hidden state and this memory. You're basically recreating that with transformers, right? And this is actually very similar to Andre Karpathy when he was talking about like an LLM computer or something like that, right? Something that is like has some memory that it's writing to and it's reading from. This is the token Turing machine, and it basically allows you to consume tokens and then store some tokens, read some tokens, and then use that to output. So you can have some memory that allows you to have more interesting behaviors, such as the behavior that Greg Brockman demoed, where he has the person, let me refresh this. He has the person come up from behind him and then do bunny ears, and then he waits until the person leaves, and then he's like, okay, did you notice anything? And the model did, right? So the model was storing that somewhere. The model was storing that in the memory. Okay. So where are we all going with this, right? Let me summarize at the end all of this. We are now on the cusp of, if you want to think of it, if you want to call it AGI, sure. I think AGI was ChatGPT back in 2021, but for people that are still on the fence about AGI, we are about to hit that, right? Because as soon as you have something like this that is consuming audio, visual, it's consuming video, it's consuming audio, and it's outputting audio and video. So it's not like it doesn't feel like you're talking to an Alexa. It feels like you're on a Zoom call with Scarlett Johansson, right? And that is going to absolutely blow people's minds when you're on a fucking Zoom call with Scarlett Johansson, you know? And based on these papers, I think that the way that we're getting there is not going to be kind of what we've been doing up until now, which is kind of like this processing each modality separately and then projecting them all and then just reusing an LLM. I don't think this is how we're going to get to talking to Scarlett Johansson on a Zoom call. I think it's going to basically be this. I think you're going to have to train these things from scratch on absolutely monstrous amounts of data. But guess what? We have that data. Think about Netflix. Think about YouTube. Think about all the videos ever made, right? Disney's like movie library. We already have that data. We already have data for audiovisual in, audiovisual out. So all we got to do is just train it. All we got to do is wait for Big Zuck to say, "Yup, do it. Launch the training run. We're gonna spend a cool $1 billion on this training run, but we're gonna get out of it one giant end-to-end model that inputs any any modality and outputs any modality." And I think once we have that, even the haters won't be able to deny it. That is fucking AGI, and I'll see you guys there. Okay. Question from Pertuge. Could you shed some light on attention norm or logit drifting? Yeah, so what Pertuge is talking about is basically one of the problems they ran into is that when you have multiple modalities coming in and multiple modalities coming out, you get this divergence effect where when training with multiple modalities of significantly varying entropy, then modalities try to compete with each other. So significantly varying entropy, what it means there is that the way that I see it, it's like images and text. Like if I give you 50% of an image, I'm outputting the rest of that image. I think is easier than giving you 50% of a paragraph and outputting the rest of that paragraph, right? So there's a different amount of entropy depending on the modality. So if your model is being trained end to end to try to just like predict and output things with the highest possible probability, it's going to be biased to specific modalities. So the way that they solve this is with what they call, where is it? Logit drift, blah, 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 core attention. We first deviate by using query key normalization, so that's a normalization, and then applying layer norm to the query and key vectors within the attention. So this is what they're calling the attention norm here. Is basically they just normalize the queries and keys, because if you have interleaved images and text, some of those cues in that sequence are going to be image cues, and some of the Ks are going to be text Ks, right? So like you have to do extra normalization there. I don't like fully understand this, to be honest. Like at the end of the day, this is kind of like alchemy, you know, like even the people who like decided to do this don't really fully understand the theoretical and mechanistic reasons for that. They just kind of like, oh, we tried this and it didn't work, and then we tried this and it didn't work, and then we tried this and it worked, so that's what we did, right? I think it's mostly that. Why are humans so data efficient while models are not? Because of like 2 million years of evolution. As we go more multimodal, small language models don't have a chance. I think we'll still have small models, right? So like this, I think we're going to have the end-to-end multimodal model running on a cell phone. Like, because you make these big models, but then you can distill them and you can prune them and you can quantize them. So there's a lot of ways to take a big model and make it much smaller. But when you're training the initial model, you do need to have a big model with big capacity in order to learn the representations that you need from this big data set. So it's like the models that you're training, those will still be big, but then there's going to be this long kind of tail of different techniques that you can use to take those big models and make them very small so they can fit on a cell phone so you can have a consumer product. Okay, people asking about coding streams. Eventually. All right. That's pretty much it. What do we think people with researchers working with smaller compute can do now to be doing meaningful research? honestly, the story, like, it's not good, you know, like the reality is that, like, I'm starting to think about this too. Like, there's a lot of things in my life where I'm suddenly like, the best solution to this problem is to just wait a year and then let the AI solve this problem for me. And it kind of feels like that in AI research right now, where it's like, here, this Hugging Face paper, right? Like, these guys put a bunch of work into this, and they're like coming up with like, oh, like, it's important that the quality of the language model backbone is important, right? And it's like, what is the point of this? This is like, does this help anybody? No, it doesn't fucking matter, because you're just going to train it from scratch end to end, right? So like, this is like a research finding that is relevant like a year ago, but now is basically irrelevant. So unfortunately, the reality is it just doesn't look good if you're doing small budget research, because it's like all the stuff that you can discover is not really going to like lead to this next level stuff. I don't know. We're all just waiting for the big companies to train these giant models, and then that's it, and we can all be freed from our prisons. Anyone working in Mojo instead of Python? I'd be curious. I saw the Mojo hype, but like, I haven't really heard of anybody using Mojo, so let's go in Ed. I want to do VLMs in my PhD. Since we can't build such architectures, what would you recommend to work on? I mean, even though I'm saying that like publishing this kind of research isn't like useful, like, don't let that stop you. You know what I'm saying? It's like, I can grow tomatoes in my backyard, not because I think I'm going to grow better tomatoes than the industrial automated agriculture. You know, I'm not going to be able to do that, but growing tomatoes in my backyard is fun, right? So it's like the same thing. It's like, if you're doing a PhD, like, yeah, you can train a little VLM, and like, it's not going to necessarily be better than these VLMs, certainly not, but that doesn't mean you can't do it. Like, you can do it and have fun and just like explore, and, you know, like, you can still do what you want to do, even if it's pointless, right? Like, don't worry about it. Don't worry about impact. Just worry about your own fulfillment. Okay. That's all. That's all I got, guys. Thank you for listening. Thanks, Arkajati, Josh, Ed, Saskia, Srimlia, Jai, JC, Hyung Sung, Christopher, Pratyush, MD, Jai, Majetti, English, Tomcat. I'm trying to make sure I don't miss anybody here. Yang, Khalil, Explorer, Swati, Druba, Julian, Ali, Old Clips, something, Druba, VR, Wizard, English, Josh, Prasuk, Kalina, Arkajati, again, Luis. Who else? Christopher, Khalil, Julian, again, Chicken P, Yang, Day, Sunshine, Akram, Eunice, Dark Matter, Exploring, and Sarah. Thanks everybody for listening. Hope you had a great time. Hope you have the rest of your weekend is also great, and see you guys later.